Good morning, everyone. Thank you so much for coming. Welcome to day 3 of Our Medicine. My name is Joy Payton, and I am one of the organizing committee of this conference. And on behalf of everyone behind the scenes, we're so glad you're here, and we hope that you are enjoying our incredibly talented speakers this week. And this morning, it's my privilege to introduce Thomas Charlon, who will be demoing some cutting-edge open source tools that his team developed to deal with the complexities of mental health diagnoses. So, Thomas, thank you. I will pass the mic to you.
Thank you very much. Hello, everyone. So I'm part of this CELEHS laboratory at Harvard Medical. We're in the Department of Biomedical Informatics. I'm with Professor Tsai, who's tenure professor since 10 years. She's also a co-professor at School of Public Health. So this is our lab page. We developed quite a few software. And today I'm going to go over 2 packages I developed: co-occurrence computation, the NLP embeds package, and knowledge graphs that focuses on the visualizations that we can obtain from those co-occurrence matrices. These softwares are developed both for the lab level, but also specifically for our mental health research project. So that is a CSRP, Center for Suicide Research Prevention. This is a web page that introduces the project. So our main focus here is to do risk prediction models.
Thomas, are you sharing your screen? I apologize. I'm not sure if other people are seeing it, but I'm not seeing your screen.
Okay, I am sharing.
Oh wait, I'm sorry. I was looking at the wrong screen. That's my error. I do see your screen. My apologies.
Thanks, great. Yeah, so these methods, I'm going to present kind of the generic way to do it with examples focusing on this research project. So last year I presented a bit similar stuff where our packages were in development and now they are on CRAN. So these are the 2 vignettes of our packages. So I can put the link maybe in chat. This is the first vignette, second vignette. And here are some links to apps that we're going to use a bit later on. And this is the link to the lab page. So if you want to get started, if you want to do some of the codes I'm going to present, you can either, if you're using Docker, you can pull this image that has some of the packages installed. Otherwise, you can build it from the GitLab repo. I'm going to put that link right here. So you can clone the repo, and once you're in it, you can use Docker build. Otherwise, you can do Docker pull of this image and install a few other packages. If you're not using Docker, you can just try to install these packages. We're also going to need to install the actual NLP embeds package. I'm going to add this here. So this script on the right is in the GitLab repo. So if you clone it, you can get it in scripts. but I'll also put a link direct here. So you can open it and copy paste directly from your. So if you open your R console, normally if you install this package, it's everything you need for this NLP embeds, and these packages below are the ones that are specific to this script and to the demo of today. These packages should install directly, and this package that we will use for the evaluation and the visualization needs the iGraph R package, which has a system level dependency on GLPK. So you might need to install this either from your command line. I guess probably in RStudio on Windows, it will ask you to install it or propose you. So let me know if you have an issue installing these packages. So maybe I can introduce a bit while everyone install these. We can have a little look at the vignette. So co-occurrence analysis will be useful for when we have patients and we have some codes. So we have their visits at the hospital. One day you might get diagnosed with a mental health disorder. Maybe it's depression. Maybe the clinician will prescribe some medication. And so our usual clinical data will be this patient on this day received this diagnosis and this medication. So this is the codified data. And we might also have the clinician's notes, which might detail why a diagnosis was made. Maybe it's saying, oh, he wasn't feeling well, he wasn't sleeping well, that's why I diagnosed this and I prescribed this. So the narrative notes, the clinician's notes usually give us more detail. And especially for mental health disorders, it's important because the disorders are very overlapping and can have many nuances. So this is the data we're usually working on, electronic health records, and it can quickly be huge databases when we have millions of patients over tens of years. So in this package, I leverage RCPP algos to do it very efficiently. And we can also do it on SQL databases for objects that don't fit into the RAM memory. This publication from our lab a bit prior to when I joined talks a bit about it also, shows some of the results we obtained. So it wasn't using my package. I kind of did a new way to wrap up all this. So as I was saying, co-occurrence, so we're going to look at which codes happen in the same time. So maybe the patient comes in for, I don't know, a fracture and gets prescribed anti-pain. And then the next month he gets admitted and he is prescribed antidepressant and is diagnosed with depression. So in the first visit, there was a fracture and anti-pain. In the second visit, there was depression and the antidepressant. So this is what co-occurrence will look at. It will look at codes that happen at the same time. So this enables us to say, okay, these codes are correlated. And if we do that on our whole patients, then we build a matrix of just the correlations between our codes. And that's when then we can say, okay, so for depression, which are the most correlated medications, and we can get the list of all the medications that are usually prescribed at the same time. So it's very similar to the Word2Vec algorithm. And so Word2Vec was more for NLP. It's basically over a text, we have a sliding window. If two words appear in the sliding window, the two words get an increased similarity. And at the end, we measure the similarities overall. And then we're able to say, okay, this word is most correlated with this word, these words. But there's a lot of similarities between Word2Vec and this co-occurrence analysis. And when Word2Vec came out in 2013, a little while after, there were some academic papers that were showing that it's actually an approximation of using co-occurrence, then PMI, pointwise mutual information, and SVD, singular value decomposition, which is related to PCA. So this is this publication talking about the fact that Word2Vec approximate these results is this Levin Goldberg 2014, and the full reference is at the end of the vignette. So Word2Vec is very good when we have a lot of input data that we can't compute the actual analytic solution precisely, exactly. It's highly parallelizable, but if our input data allows it, it may be better to do the actual analytic solution. It can give us more stable results. Word2Vec, we can increase the number of iterations with Word2Vec, but maybe it's just better to do the analytic solution. So here I'm giving a little example of what our data set would look like and what the co-occurrence will be. So we have a few patients, here 4. We have the months where they were visiting the hospital, and we have the codes that they had in the database. So it can be a prescription, a diagnosis, and the count, the number of time it occurred during that month. So doing a co-occurrence on that gives us this data frame. So for example, C1 occurred with itself 16 times. We can see here, first code, third code. And so here we can see C1 and C2 co-occurred 7 times. So it was in months 1, in patient 1, we had these two, C1, C2. So we take the minimum between their frequency. So this counts as 1. Patient 2 only had C2 during months 1. And so over here, we can see patient 1, month 3, C1, C2, 6, and 7. So here we take 6, and then we sum up 6 and 1. This gives us the co-occurrence of C1 and C2 at 7. So this is just a co-example to show that the co-occurrence is computed correctly. This explains what I just said. This decomposes a bit. Okay, so now we have our co-occurrences. We can compute pointwise mutual information. And then we can compute the singular value decomposition. we give a number of dimensions, like in PCA, and we have a representation of the codes along a number of dimensions. So this is what we call an embedding matrix. So instead of having a symmetric matrix of maybe 1,000 codes, we usually have maybe around 5,000 codified features, and NLP features can be up to 50K, and we usually do a feature selection, just select some relevant ones. So we're usually at 20K, between 10 and 20K NLP feature. So we go from a matrix of around 20K by 20K to 20K by the number of dimensions. And so very correlated codes will be will be represented as a linear combination in one embedding dimension. There are some considerations on the number of dimensions we might want to use. We don't want a too high number of dimension, but we want a high enough so that it can embed the nuances in our data sets. And we can use known pairs to measure the performance of the embedding matrix. So known pairs will be pairs of concepts we know are related. So for example, antidepressant and depression, or two diagnoses, schizophrenia, psychosis. So these pairs of concepts enable us to then, once we have our embedding matrix, we determine a similarity threshold, and we're able to say, okay, there's 80% concepts that were correctly predicted, and we can derive an AUC from that. So we can use this AUC to guide the number of dimensions we want. This is what I'm saying here. We should balance the number of dimensions between a high AUC and a lower number of dimensions. This was a bit the theory of the co-occurrence analysis. The vignette goes on to explain a bit how to use it on SQL files. And then how we can subset NLP features to relevant codes. If you have a problem installing RCPP algos, you can try installing the 2.4 version. So in this demo, I'm going to show how it compares to Word2Vec on a dataset of open access publications. So we did this analysis to derive the important features we wanted to have a look at. So if you're all installed, you're in the folder that you cloned from the Git repo. Should be able to use these 3 lines. In this file, there's a few functions I defined just for the script. And so here we have a call to Europe PMC. We're going to download some open access publications. It can take a little while to download them. Should be fine, I guess, but I copied them here in case. So we first search and get their identifiers. Then we actually download them. This is what's going to take a little minute. I was thinking maybe if there's a lot of people downloading them at the same time, it might take a bit more. So that's why I added the file on GitHub, there on Dropbox. This is the Dropbox link. You can either download it and load it, or here we have a call to wget. I'm going to share again here is a link to the script, and can go back up to the repo. Still downloading. So here we're searching for a title that matches suicide attempt, and that is an open access publication for which we can download the full corpus. Often such analyses on scientific literature can also be done just on the abstract. Here I'm trying to do it on the full text. So we see that it's finished now. And with the PyDPMC package, we can parse the output. It's actually XML files. So this is the parsing. We can have a look in our output object. We have 99 objects. Each object is a table. The first column is the section information, paragraph, sentence, and text. So each the text is separated in each sentence. So as I'm saying here, now we have to pre-process the text before calling Word2Vec on it. So we're first going to show how we call Word2Vec, and then we're going to compare with co-occurrence analyses. I'm doing this because often EHR data is not publicly available. So here I'm showing how we can transform it as a EHR data. So to pre-process the text, there's a few different strategies. In our lab, we use the Nile software. There's the link just here. What it will do is that it has a dictionary with some words or n-grams, so several words, and it will assign it to a unique identifier. So it's freely available for academics, but it does require you to enter your email, so you might not be able to download it immediately. So in this demo, I'm just going to show how we can do more easy approach to text pre-processing. But in our analysis, we usually use NAT. So the more classic approach that you can find in some textbooks, removing stop words, performing a bit of stemming. So stemming is when we remove plurals or denonyms. So denonyms can be like verb inflections. So these are the functions that are defined in the second script file that we just sourced. This is the function we're going to call that we define in the script file. You can have a look. So one thing it will do is that it will remove irrelevant sections from the open access publication. We're going to remove a bit of punctuation. We don't want to remove everything because there might be some dashes in words that we want to keep. For example, COVID-19, we don't want to have COVID and 19, we just want to keep them together. So once we call this on our full text, then each object is a huge text. We lost the sentence information. It's just one long character string. So this is process. It's suitable for downstream analysis, even of n-grams. And then there's the second set, there's the second one, prune text, which will focus just on single word analysis. Prune text will actually do the removing of stop words and stemming. So we can see in this example that we still had the very common words of, these are some of the words that will be removed. Another example is here, we can see a plural, interventions. So the prune text function is running. Okay, it's done. We can have a look. So now we can see that our big character string has all the stop words removed, and we don't have so much plurals. There might be a few that are remaining, but most are taken out. The list of stop words is from the TM package. Here you have the full list of all the words that are removed. Okay, so now we have our 99 publications that are pre-processed and ready to be used with Word2Vec. So this function is to our vectors, is a wrapper call to Word2Vec from the text2vec R package. It will combine a few of the usual functions that are demonstrated in the vignette of text2vec. So we first tokenize, we create our vocabulary. We can apply some filtering on term frequency to remove very rare words. Then we create the term document matrix. And then we call Word2Vec. And this is to get the embedding matrix from the Word2Vec fit. We have 10 iterations. And the output. So we have our words in rows, and 100 is the number of dimensions. So if we have a look at the row names, these are all our words that have a frequency higher than 10 in our full corpus. And we can have a look. This is what the very beginning of the matrix looks like. So each word has a numeric representation in each of the 100 dimensions. Here I added some information about the results I obtained when doing it on a larger set of publications. It shows the influence of the term frequency threshold, because as you put it higher, you restrict the number of, you have less terms in your matrix, and it's easier to predict relationships correctly because the more frequent words gives you more robust. And so if you have a word that just appears a few times, obviously it's hard to predict correctly what it means. But you do also lose a lot of relations. You lose a lot of concepts. So there's some fine tuning to be done here. And here I show, so if we have term frequency of 3, maybe we have an AUC of 0.6. And as we increase the term frequency threshold, we increase our AUC, but we also decrease the number of terms we have. So in our use case, we're trying to do some feature selection, but we wanted to have something that is a bit in between. So I talked about these known pairs. Now we're going to have a look at what they actually are. So in the inst folder, there's an open access comparison that's tailored just for today. This is an extract of the pairs we're using. This is just for this example here. Usually our known pairs are much longer. Here I was saying we have something like 20,000 relations. So here we have relations for terms that appear in our data set here. You can see a bit what it looks like. So here, this is a medication name. So we have our embedding matrix. We can compute cosine similarity on it. And then we try to find an appropriate threshold that predicts correctly these terms. So we're hoping that these two terms have a cosine similarity high enough. We set a threshold to say all the terms that have a similarity above, we consider them related. All those below, not related. And then we compare the list of related concepts to our known pairs. This is how we get an AUC. So this is done with the K-graph package. So here we can see, okay, we had 268 known pairs. We can predict with an AUC of 0.65, which is not so great, but still already better than random. And for a data set of 100 publications, it's quite good. We usually have much more. And as I was saying here, we can get up to 0.8 if we have a very high threshold on term frequency, which is much more reasonable. So this is the example of using Word2Vec to predict relations between concepts using the 100 publications. Here's a little detail about the maximum concepts parameter. This and the return object, we have the actual cosine similarity threshold that was used for determining a number of false positives. Well, I'm not going to go too much in detail as I want to go on. So I see in the chat, so this is for single words. So this example is just for single words. For multiple words, we could either use n-grams, but it becomes very computationally intensive. And what we usually do to use multiple words is that we use the Nile software with a dictionary. So instead of considering all combinations of words, we just have a list of medically relevant terms. This comes from UMLS, Unified Medical Language System. And This Nile dictionary is available on the software page. That is linked above. Over here. So I do recommend you to try downloading it to see, but you'll probably not be able to download it instantly. Or maybe if you have a edu email address, it should be fine. If you don't and you're still an academic lab, you can email us. Okay, so I was saying now we have our knowledge graph objects. And what we have been using it for is that now we want to know a list of words that is related to our disease of interest. So we can search for all the terms that contain the words listed in our words. We can see a few here. We can say, okay, we'll want to try the 3 last one. So we can write those in a variable. And here we're going to take all the words that are related to these 3 words. So it's all the words that have a higher cosine similarity than the threshold we determine with the AUC. So this is our data frame. Combinations of words with our 3 of interest. And then we can take the union and say, okay, these are all suicide relevant terms that we want to have a look at from the clinician's notes. So our co-occurrence analysis can be very huge if we consider all the words. And with this list, we can say, okay, we're going to have a look just at these words. So in the NLP embeds package, there's I added 2 such lists of words. These are here. So the second one is one I did only on suicide publications. We have 5,000 WHOIs. And the first one is general mental health, where we have prox 15,000. So this was with Word2Vec. Now I'm going to show how we can do the similar analysis with the NLP embeds package by using the analytic solution. So we're going to do a slightly different approach on processing the full text. We're not going to collapse every sentence together. So here, each document, we kept the sentences separated. But we still unlist everything. We're not going to compare document, we're not going to consider them on document level. We can call the prune text function. And this is a little function I did in the script file that will transform these sentences to the actual format the NLP embeds is waiting for. So we can have a look at what it looks like. So the columns are strict, so we need to call them patient, parent code, months, count, but we can actually just put in, so the patient will be the document, parent code, the word, months will be the sentence, and count the actual count. So this package was developed for EHR, so that's why I put these column names, but I'm showing here how we could use it other kinds of analyses. So this diagram is quite long, 200K rows. The only important thing is that patient and months, we will only consider co-occurrence between a similar patient and a similar month. So apart from that, you can just write the sentence ID in the patient or vice versa, doesn't matter. So we can call build df co-oc on this object. We use the same term frequency. This is our sparse matrix. We call PMI on it, and then SVD. This is a little fix. I'll put row in. And we can recall the knowledge graph function. And what we see here, AUC 071. So we increased our performance compared to 0.765 before. As I'm saying here, the comparison is not totally fair. The word to vec was done on 20-word sliding window. Here is between sentences. Also, we kept the sentence information while word to vec didn't. But still, it shows that we might prefer to use this analytic solution. And so now we can, this was the NLP embeds part for the computation. And I'm going to show a bit how we can use the K-graph package also to visualize it. So you can save the object like this. And so now we can spin up one of the two web pages I shared. I'm going to share them again. So they are, one is a slightly more updated version, but we can use either one. So these are the objects. So this is the object we just saved, and this is another important part, the dictionary which will enable us to get some colors and some labels. But just with the embeddings, this is what we can get. So we will have a look at how our concepts are related. By default, it just selects some two random words, but we can focus on, maybe we want suicide, maybe we want to see the link with PTSD. I think maybe this one. Okay, so STB, suicide thought and behavior. In publication, we'll often have rather the acronyms because the term is defined at the first, and the acronym is defined at the beginning of the publication, but for the rest of the publication, it's actually the acronym that is used. So it's often better to just use the acronym. So here we can see some of the concepts that are associated both with PTSD and with STB. So here we can see ADD, attention deficit disorder. So here I have a negative view, but normally it would just be white, and there's a slightly different colors for edges that are shared between the two concepts. So here it's very hard to see almost, and on the white version, it's a bit easier to see. But so it indicates that these nodes are not shared between the two. It's only the ones that have dark edges.
We can also click on a node for it to appear only those that are related. And so here we can see that if we click on this one is still selected, but if we click on this one is not selected anymore. And as I was saying, an important part is the dictionary. So our embedding matrix has our row name, has our words in the row names, and we can either add some longer labels, either add some group information and colors. So the dictionary data frame that we can use would look like for each row, each word is a row. We have the ID, which is the row name in the embedding matrix, the description, and then we can put a color and a group. So I prepared this with the RML dictionary. So here we have a more cool to watch graph. These are all the kind of different groups of words based on our dictionary. Here we have some nodes that are shared in between. So if we click on ADD, for example, we see that this is the group. I have a group mental process. In these apps, we can also we can upload the pairs file to be able to have the exact number of false positives. So we can decrease the number of false positives to keep only the most relevant terms. It will declutter a bit the output, keeps only the ones with the highest similarity. So this is with the Kgraph package. Here it's embedded in a Shiny app, but it's also, there's also just the functions that we can have. So the knowledge graph vignette details a bit how to use these functions. Here I demonstrate, okay, we have a data frame, we have two concepts. This is the weight, so it can be the cosine similarity. I show how to build the iGraph object and then visualize it with this function. So it's Sigma GS underneath. And I wrote a dedicated R package just to do the HTML widget, and Kgraph calls this. So we can either use directly a data frame of relationships with their similarities, or we can use directly an embedding matrix like we're using here. And this is another example with a suicide-related database. So I see in the chat. So if you want to do label concepts, so the question is it possible to train so that label concepts can be associated with value concepts? So not if you're doing an embedding matrix between words, but here in the vignette in the first part, I'm showing how to do it with directly a data frame. So you could have first column your label concepts and second column your value concepts. Here it's actually what's done with the first concept is the disease and the second concept is the SNPs. And the weight is the
minus log 10 p-value association. Was that, I hope I answered your question. So this is the core of what I wanted to show today. We can stop a bit for some Q&A. Put the links again.
While people are thinking of their questions, I just want to say thank you so much for a really compelling presentation. It's really challenging to make software that is both very functional and also elegant and attractive. And I think your team has really achieved that. So thank you so much for showing us this work. It's very, very impressive. I'm going to let folks ask their questions in chat, or feel free to come off mute. In the meantime, I am going to make Thomas the host. I need to step away to start the next meeting. So thank you so much for this presentation, and I'll let you continue the Q&A.
Thanks a lot. These are some images I prepared. If we tune a bit the parameters from the app, so here I included a lot of terms in the concepts to show. So we can have something similar by adding here BPD, borderline personality, schizo. We can change the layout type. So this is a bit closer to the screenshot I had. What we can see here, for example, is that BPD has much more concepts in common with suicide thoughts than with schizo. So again, this is just done on 100 publications, but it does give us a sample. Here's another screenshot where I'm focusing a bit more on cognition-related concepts, so self-esteem, personality. And maybe I can show you. So this is one of our apps based on these packages. So this is one of our actual results from patient EHR. Here we are looking at adolescents. We have around 9,000 patients, both codified data and NLP. And we have our suicide diagnosis in the middle, which would correspond to suicide attempt. So as I was saying in the abstract, the NLP can help us both to predict better, but also to interpret. One of the example is in our predictive features with codified only, we had acetaminophen that was springing up as a predictive value, so associated with suicide attempt. And our clinician was telling us, oh yeah, but it's just a mild pain reliever, like Tylenol, I think is the brand name. So it's probably not relevant. It's probably just noise, spurious correlation. And what we can see here in the NLP is that acetaminophen appears with overdose and with intoxication. So it kind of makes us think that there's maybe a true predictive value. It's maybe not just a spurious correlation, maybe it's actually more than that. And another clinician was telling us that what we as adults see as, oh, it's just a mild medication, it's not used as a mean of suicide attempt. Maybe for adolescents, they don't see it that way, they don't know about it, so they might still use it. And so sometimes when we interpret these features, it's hard to put yourself in the mind of someone else who has less knowledge. And so this is one example of using the NLP to drive your interpretation of features. Yeah, so I see in the chat, I was about to ask about age stratified view. You will need to recompute the co-occurrence with your new cohort. So you need one co-occurrence for the full population or for the adults, one co-occurrence for the pediatric. And this is what we have here. We have different types of cohorts. So here we have MJ general. So for our full population, it's only codified data.
Oh, yes. And medications. Mm-hmm.
And here we have MJ pediatric. One difference we see is alcoholism relation, which is much stronger in the adult population than in the adolescent population. So adolescent is from 10 to 18, so you might still have some alcohol disorders in the older adolescents. So it does explain why you still see it a bit in the pediatric population, but it's the signal is still much stronger in the adult population. So we're coming up to 1 hour. Going to say thank you to all the attendees. Hope you learned a lot. Remind, so these are the two packages, NLP embeds and K-graph. And you can hit me up if you have any questions. Bye, everyone.